Today we are going to continue in chapter number 7 regarding the internal forces. Last time we learned how to calculate the internal forces at a specific point. But today we need to know how to know the variation of the internal forces along entire beam. And in order to do that, we need to formulate shear and moment equations and then to draw the diagram. But before that, it's very important to know what does it mean by beam. When we say that this rigid body is a beam, it means that the rigid body is going to support the load applied perpendicular to their axis. So if you are going to assume this line here represent the major axis for the beam, then the load here is going to be perpendicular to the main axis of the beam. That is how the beam is going to take the load. So if I'm going to have a beam, that means the beam is going to carry that load by the load is going to be perpendicular to the main axis. The beam usually is going to be straight and is going to be long. So the beam is going to be straight and the long, and the cross section is going to be constant. So the cross section here is the same as here, and the same as here, and the same as here. And we call this beam. And we have different names for the beam. It depends on the support. So in this case here, we have pin support at this end, and at the other end we have ruler support. If this is the case, we are going to name this as simply supported beam. So when we say that we have simply supported beam, it means that it's pinned at one end and we have a ruler at the other end. Also, we have the cantilevered beam. In that case, the beam is going to be fixed at one end and the other end is going to be free. So usually we are going to face simply supported beam problems a lot, and also we are going to face cantilever beam problems a lot. When we say simply supported beam, it means that at one end I have a pin support, at the other end I have ruler support. If I said that we are dealing with cantilever beam, that means at one end we have fixed support and the other end is going to be free. Again, the beam is going to support the load. The load is going to be perpendicular to the main axis. Usually the beam is going to be long and is going to be straight, and the cross-sectional area is going to be constant. And also, in order to design the actual beam, here I have a beam. I need to design the beam itself. So in order to design the beam, in order to put the size, the suitable size, in that case, I need to know the variation of the internal forces. So I need to know how the internal forces is going to vary from that point to that point and from that point to that point. So if I don't know how the internal forces is going to vary along the beam, I will not be able to come up with the convenient design. So as engineer, I need to come up with economical design. The design should not be more than it's required, and also it should be safe. So I need to come up with a design that can carry the loads. And in order to do that, I need to know the variation of the internal forces, mainly the shear force and the bending moment. Last time we'll learn how to calculate the shear and the bending and the normal force at a specific point. For example, that point or that point and that point. But this time we need to know all the values along the axis of the beam. So in order to do that, again, we are going to use the method of sections. So last time we used the method of section. Here we are going to use the method of section in order to know the variation of the internal forces. So you need to cut here in order to know the internal forces. And again, if I want to know the internal forces here, I need to section that point. And also I need to section that point. So in order to know the variation, of course, we are not going to calculate the internal forces at all the points. For example, I'm not going to section here and here and here and here. It's going to be impractical to do that. So here, in order to solve that problem, we are going to section a beam at an arbitrary distance x from one end. So for example, instead of cut here and here and here and here and here, I'm going to come up with only one section, and the distance is going to be a random distance. So we are going to cut a section at a random distance, not at a specific point. So for example, I'm going to cut a section here, and the distance is going to be random distance. We are going to call it x1 for example. Then after I cut the section here, I'm going to apply the equation of the equilibrium for that segment. So that segment here, x, is going to represent the region from here and to here. And we are going to learn that we cannot use only one section to represent the whole beam, because we have discontinuity for many situations. For example, the concentrated force here is going to create discontinuity situation. So it's okay to represent the section by that region here by only x1, but that region here it cannot be included by the region there. So I need to have another section at that region in order to know the variation in this region here. So once I got a section x1, then I will be able to use the equations of equilibrium in order to know the variation in that region here. Then in this region, from this point to that point, I'm going to apply the equation of equilibrium. And of course, the value of the shear is going to be a function of x. And also the value of the moment is going to be represented as a function of x. So if I know x, I know the value of the shear. The same goes for the moment. If I know the value of x, then I'm going to know the value of the moment. So in general, the internal shear and bending diagram function will be discontinuous. Like I said, it's not always the case that I'm going to get one section by only one x in order to know the variation. I have discontinuity, and that discontinuity, like when you have distributed loading. Here I have distributed loading. Then the distributed loading is going to change at that point. So here I have discontinuity. So I need to take another section in order to represent that region here. Then I'm going to have concentrated force, and also that concentrated force will create discontinuity. Then I need another section in order to represent that region. So whenever I have points of discontinuity, it means that I need to have a new section. Because of this function must be determined for each segment of the beam located between any two discontinuities of the loading. So here we have discontinuity. This means that I need to get section here and section there. Here also I have discontinuity. That means I have section which I already have done that, and also I need section here. So in this case, we have two discontinuities. I have one here and I have one there. So I need to have section here and section here and section there. For example, we are going to have three segments. We are going to have x1 for that segment from here to here. I'm going to have x1. Then from here to here, I'm going to have x2 for that region. And for that region, I'm going to have x3. So x3 represent this region here, and x2 represents this region here, and x1 represents this region here. And of course, I'm going to describe that segment by v and m. V and m, they are going to be a function of x, the same here and the same here. So the equation here, it's only valid for that region. I cannot use it for that segment. And the equations which I'm going to develop from that region, it's valid only at that region. Then if I come up with expression for the shear and the moment, then I'll be able to draw the shear diagram and the bending moment diagram. So in the shear diagram, we are going to have x-axis here. We are going to have the distance. The distance is going to be from here to here. So for example, the distance here, x equal 0. The distance here, x equal a. Here, the x equal b. And here, x equal l. So in the x-axis, we are going to see the distance. In the y-axis, if I'm dealing with shear diagram, here it is going to represent the value of the shear. The value of the shear is the force. So in this diagram, we can see that the shear here is very high. At that point, the shear is going to decrease because of the distributed loading. Then the value of the shear here between A and B, it's constant, and the value is positive. All the positive value is going to be plotted above the x-axis. All the negative values is going to be plotted below the x-axis. So here we have a constant value for the shear, and the shear here is negative. Then regarding the bending moment diagram, also we need to draw the distance in x-axis, and in the y-axis we need to put the moment. Here we can see the variation of the moment along the x distance. So the moment here is 0. The moment here it has a certain value. Then the moment here is going to increase. Then the moment here is going to decrease. And at x equal L, the value of the moment is 0. So what we want, we need to develop equations as a function of x, and then we are going to draw the shear diagram and the bending moment diagram. So now, as a designer, I can see the variation of the shear. So I know that here I have a high value for the shear. Here the value of the shear is going to decrease, and I know that the value of the shear here is negative. So using that diagram as a designer, I'll be able to design the beam. And also I'm going to use the bending moment diagram. From that diagram, it's clear that the maximum value it's here, and at that end the value of the moment is 0, and the value of the moment here is 0 as well. So once I know the shear diagram and the bending moment diagram, I'll be able to design the beam. That is why learning how to draw the shear diagram and the bending moment diagram, it's very important. And you are going to do that many times in your advanced courses. So the objective of that lecture, we need to show how to form the equation of the shear and the bending. We say that those equations, they are going to be a function of x. And then we need to learn how to plot the shear and the bending diagram. So here we have a beam. We are going to make sections according to a certain, according to arbitrary value, random value. And in order to know the random values, it depends on the points of discontinuity. Then once I develop the equations for the beam, I'll be in a position in order to draw the shear diagram and the bending moment diagram. So how I'm going to do that? Here we have some steps. If you are going to follow those steps, we are going to be able to draw the diagrams. The first step, I need to evaluate the support reactions. So I'm going to have a beam. The first step, I need to determine the support reactions. And we learned from the previous lectures how to draw the, determine the support reactions. So we need to draw the free body diagram, replace all the reactions by, we need to replace all the reactions by support reaction by reactions, and then we need to apply the equation of the equilibrium in order to know the unknowns. And step number 2, we need to get the shear and the moment functions. We say that we need to know the points of the discontinuity so that we can know where to cut. Where we are going to have a section depends on the point of the discontinuity. We have 3 situations for that. The discontinuity points, we are going to have a point of discontinuity when a distributed load changes. So we need to take care of distributed loading. And also when we apply concentrated force, and also when we are going to apply couple moment. So if you apply couple moment, we are going to have point of discontinuity. If you are going to apply concentrated force, we are going to have a point of discontinuity. And also when the distributed loading is going to change, also we are going to have a point of discontinuity. So we need to take care of that so that we can know where we are going to put, or where we are going to have our sections. So then we need to section the beam at distance x. Again, depends on the point of the discontinuity. And then we are going to draw free body diagram for each segment. And also we do not forget to put the positive senses. And then after that, we are going to apply the equations of the equilibrium. Mainly, we are going to apply the summation of the forces in y-axis equals 0. And we are going to take the moment at the end of the section. Finally, if we manage to get the equations for the shear and for the bending, we will be able to draw the shear force diagram and the bending moment diagram. For the shear force diagram, where it's going to be a diagram V versus X. In X, X represents the distance, and V represents the value of the shear. And for the moment, bending moment diagram, X represents the distance as well, and the Y represent the moment. If the values above the X-axis, the value is positive. If the value below the X-axis is going to be negative. And regarding the sign convention, is going to be the same sign convention that we have got in the last lecture. So if you are going to work with the left part, the positive sense for the shear is going to be down, and for the moment is going to be counterclockwise. If you are going to work with the right part, the shear is going to the shear which is up is going to be positive. The moment that rotate counterclockwise is going to be negative. So now let's solve example so that we can connect all the concepts that we have discussed here in that lecture. We are going to follow steps in order to draw the shear force diagram and the bending moment diagram. So here we have simply supported beam. It's simply supported beam because at one end, the support, we have a pin support here at A. At the other end we have ruler support. So this is simply supported beam. And we have concentrated force exactly at the middle. The span is 4 meter, the length of the beam, and it's required to draw the shear and the moment diagram. Again, we say that in order to design the beam, it's important to know the shear force diagram and the bending moment diagram. Without that, you are not going to be able to design that beam. So let's see the first step. The first step, we need to determine the support reactions. So we need to determine the support reaction. Now you should be expert. You have many examples in order to draw the support reactions. First, as you know, we need to draw the free body diagram. Here we have pin support. We should have AY and AX. Obviously here AX is going to be 0 because we don't have any forces in the x-axis, so we don't need to include it here. The ruler here, we are going to have reaction in Y. We are going to call it CY. So now we finish with the free body diagram like we have learned from the previous lectures. Then we are going to apply the equations of the equilibrium. Like I said, if you are going to say that summation of the forces in x-axis is going to be 0, that means AX is going to be 0, so I don't need to include that. Then if I'm going to say that summation of the forces in y-axis is going to equal 0, then I'm going to have two unknowns, so it cannot be solved. Then I'm going to move to the third equation, which is the moment about any point should equal 0. So I can take the moment here or here. It doesn't really matter. If you are going to take the moment at A, then you will be able to determine CY. If you are going to take the moment about C, you will be able to determine the you are going to be able to determine the reaction AY here. So I'm going to take the moment about C so that I'll be able to know the reaction AY. So if I'm going to take the moment here, if you draw the line of action, AY is going to be multiplied by 4, and it's going to be negative because the rotation is going to be clockwise. And here I have 5 kilonewtons. If I'm going to draw the line of action here, the perpendicular distance is going to be 2, and it's going to rotate counterclockwise, which means that it's going to produce positive moment. So here I have positive moment, 5 kilonewtons times 2, and here I have negative moment minus AY times 4 meters. So here I have one unknown and one equation. I can easily solve for AY. So AY came out to be 2.5 kilonewtons. So now I know the reaction AY. Then I'm going to apply that equation, which is the forces in y-axis going to be 0. Here is the sign convention. Then I'm going to end up with AY plus CY equal 5. So I have AY plus CY. This one is minus 5, so I'm going to move it to the right-hand side. It's going to be positive. And since I know AY, that means CY is going to be 5 minus 2.5, which is 2.5. And those value really make sense, because if I have 5 kilonewtons exactly at the middle, that means the reactions here is going to be the same. So in the beginning, if you are going to have experience from solving, it's obvious that since the concentrated force located exactly at the middle, then the value of the reaction, they are going to be equal. So if I'm going to have 5 kilonewtons is going to be carried by 2.5 here and 2.5 there. So now here I have 5 kilonewtons. I have reaction here 2.5 kilonewton, and here 2.5 kilonewtons. Now we finish from the first step, which is the determining the support reactions. Now we are going to move to step 2, which is the shear and the moment functions. Now we need to develop function for the shear and the moment. In order to do that, we need to cut a section. So I need to cut a section for that beam here. And in order to do that, we say that it's important to know the points of the discontinuity. Here in this example, we don't have distributed loading, and we don't have couple moment. We have only concentrated force. So that concentrated force here is going to create this continuity. It's mean that I need to cut a section before 5 kilonewton and cut section after 5 kilonewton. So here is a point of discontinuity. Then in order to cut a section, I need to cut a section before that point and a section after that point. Sometimes I say to the student, in order to understand this, if you are going to cut a section here, or a section there, or a section there, will that make any difference if the distance is going to be x? So I'm going to cut a section here, and the distance is going to be random, but within that region. That means the value of x here, it should be equal or more than 0, and it should be less than 2. Because at 2, I have a point of discontinuity. So here, I'm going to put x. So I'm going to cut somewhere in that segment here, x. Then at the end of the section, I'm going to put the shear and the moment. Take care of the positive senses. The positive sense is down, and here is counterclockwise. Just focus on that segment here. We have the reaction, we have the distance x, we have v, and we have m. If that section was here, will that diagram is going to change? Of course not. I'm going to get the same diagram because the distance is x, and here I don't have any variation. If the section was here, will that diagram is going to change? No, because the distance is x. If I'm going to develop equation, the equation is going to be the same. So I need to get only one section for that region. But if you are going to cut here, are you going to get the same section? No. You are going to get the section like that. So if you cut here, or you cut here also, you are going to end up with the same section. So that is why for that region, I'm going to have only one section. It's going to be here or here. It doesn't really matter. You are going to get the same segment. Then for that area here, also if you cut here or you cut here, you are going to end up with the same segment. We have x. The x, it could be 0 or it could be a number less than 2. X in that region, it could be more than 2 or 4 or equal 4. So if you are going to develop formulas here, then that formula is not valid. It's only valid for that region. If you are going to develop formulas here, the formulas is going to be valid only in that region. So now let's work with the region AB. So in region AB, we have one section at X. Here, we need to know the value of V and M. Of course, the value of E and M, we are going to expect that the value is going to be as a function of X. So let's see how to do that. In order to know the values, we need to apply the equations of the equilibrium. In order to know the value of V, I need to use the summation of the forces in y-axis. And here is the sign convention. So if I'm going to apply that formula here, I have 2.5 is positive according to the sign convention. The value of V here is negative according to the sign convention. So I have 2.5 positive. I have the value of V negative. I have one equation. I can solve for V. V equal 2.5 kilonewton. You can see here, even though we cut at a distance x, the formula is constant, which means that in that region here, the value of the shear is going to be constant, which is 2.5 kilonewtons. Then, in order to know the value of the moment, we are going to take a moment at the end of the section. So the moment is going to be here at the end of the section. And do not forget the sign convention. So if I'm going to get the moment here, I'm going to have m, which is positive. 2.5 is going to cause a moment counterclockwise by the distance x. Again, the x, it could be from 0 to 2. So I have the m, which is positive. I have a moment 2.5 times x equal 0. That means the moment is going to be 2.5x kilonewton meter. So again, here in the equation of the moment, the value depends on x. So for example, if x is 0, that means the moment is 0. If x is 2, the moment is going to be 5. If x is 1, the moment is going to be 2.5. So now I have equation. If I know the value of x, I'll be able to know the value of the moment. Now let's move to the other segment, the region from B to C. Remember, here we have two segments. The first segment from A to B, the second segment from B to C. So we got expression for that segment here, and now we need to get expression for that segment there. So we finished from that one, and now we are working with the segment BC. Again, I'm going to apply the equation of the equilibrium. In order to know the value of V, I'm going to use the summation of the forces in y direction should equal 0. Do not forget the sign convention. Then 2.5 is going to be positive, 5 is going to be negative, and the shear is going to be negative. So this one is positive, this one is negative, and this one is negative as well. I have one equation. I can solve for V. V came out to be minus 2.5, which means that since the value does not have anything to do with x, that means the value is constant, and the value for all of this region is going to be minus 2.5. So in region between 2 and x, the value is going to be minus 2.5 kilonewtons. Then, in order to know the value of the moment, I need to take the moment at the end of the section here. So in order to do that, it's very important to put the sign convention. The value of the moment is going to be positive. Here I have 2.5. It's going to cause a moment if you are going to multiply it by the distance x, and it's going to be negative. And here we have 5 kilonewtons. The distance here is going to be x minus 2. So any distance here is going to be x minus 2. Remember, the x start from 2. So we are going to start from here. Then that force is going to cause a moment. Draw the line of action. Then you multiply by the perpendicular distance, which is x minus 2, and it's going to be positive. So I have m, and I have 2.5 times x is going to be negative, and I have 5 times x minus 2 is going to be positive. I have m positive, 5 times x minus 2 is going to be positive as well, and 2.5x is going to be negative. Remember, here is a point of the rotation at the end of the section. Then, if you are going to simplify that formula here, you are going to find out that m, the moment in this region between 2 and 4, equals 10 minus 2.5x. You can see here the moment, the value of the moment depends on x. Once I know x, I know the value. For example, if I want to know the value of the moment here. So at that region here, I need to x should be, for example, 2. So if x here is 2, then what you will get? You will get 10 minus 2.5 times 2, which is 5. So the moment here is going to be 5. What about the last point at 4? At 4, you are going to find out the moment equal 10 minus 2.5 times 4, which is 0. So I have expression help me to know the value of the moment at any distance, but here it should be only valid for that region. So now I'm in position in order to draw the shear and the moment diagram. First, I need to draw the free body diagram with all the forces. We determine the reactions. Then I need to draw a line of action for the forces, like that. Then I'm going to draw the x-axis. X-axis here represent the distance. I need to draw the right axis. Y-axis here represent the shear force. Again, I need to draw another diagram. I have the x represent the distance, and in y represent the moment. Here I'm going to draw the shear force diagram, and here I'm going to draw the bending moment diagram. I need to put the equations from region AB. So I have region AB. I develop those equations, and those equations are only valid for this segment here. When x is more or equal 0 and less than 2, which is here, and I need to recall the equations for the part BC. So those equations valid only for that part, and those equations are valid only for that part. So remember those equations between 2 and 4. Now I need to draw a diagram for the shear. In order to draw the diagram for that region, I need to use that formula. Here, regarding the shear is constant. It does not depend on the value of x. That means from here to here, the value is going to be constant and is going to be 2.5. And the value is positive. Since it's positive, it's going to be drawn above the x-axis. Okay, so here we have v equal 2.5 above the x-axis, because the value here is positive and the value is constant. Then for the region between B and C, I'm going to use that equation here, because we say that in that equation, in that part BC, I'm going to use the equation from here. And the value of the shear, again, it's constant, but it's negative. That means the shear from here to here, we have constant value, but it's negative. Since it's negative, it's going to be drawn down here. So the shear here is minus 2.5. Now I'm done with the shear force diagram. So the shear force diagram shows us that if you are going to take a section here, the shear diagram is going to be 2.5. If you are going to cut it here, also is going to be 2.5. If you are going to cut it here, it's going to be minus 2.5. If you are going to cut here, it's going to be minus 2.5. So now I know the variation of the shear force diagram, which is our goal. Then we need to do the same thing for the bending moment diagram. Again, for region AB, I'm going to use that equation, m equal 2.5x. So now the diagram depends on the value x. So how I'm going to draw the diagram in that region? Like you can see here, that equation is the equation of the straight line, is the equation of a line. And we know that the equation of the line, if I know 2 points, I'll be able to draw the line. So here I have a line, but I don't know how to draw it. If I have 2 points, for example, if I have the values at that point and the values at that point, I'll be able to draw the diagram here. So I'm going to say that at x equals 0, here, the x equals 0. I'm going to substitute 0 here. If x is 0, that means the moment is going to be 0. So the diagram here is 0, 0. 0 for the x and 0 for the moment. Then I'm going to substitute the value of x here. X at that region equal 2. So I'm going to apply 2 here. If you apply 2 instead of x, the moment will equal 5. So here I have 0, 0. Here at 5, I have at x equal 2. The moment is 5. So I have that point and that point, then I'm going to draw a straight line. So because I know the equation here is the equation of the line, if I'm going to know that point here and that point here, and I'll be able to draw the free body diagram. Now we finish from AB. What about BC? In BC, this equation now it's not valid for that region. So I need to use that equation. So here I have the moment equal 10 minus 2.5x. Again, it depends on the value of x. And again, this equation of the line. If I draw 2 points here and here, I'll be able to know how to draw the line. Then I'm going to substitute when x equal 2. So here x equal 2. If you put 2 here, then the moment will be 5. So the moment here is 5. And if you apply that x at that point, which is 4, in that equation, we are going to have 10 minus 2.5 times 4, which is 0. So I have 5 and 0. So here is 5 and here is 0. So now I managed to draw the bending moment diagram. Again, the bending moment diagram, we're going to show us the variation of the moment. So the moment here is 0, the moment here is 0, the moment here is the maximum value, which is the 5 kilonewton meter. Then when we are going to design the beam, I'm going to use this maximum value in order to design the beam. And here I'm going to use the value of the shear in order to design the beam as well. If you are dealing with reinforcement concrete, then the moment you are going to put additional bars here regarding the shear, you are going to put straps at the end here. So I'm going to stop here. If you are going to have any questions regarding